Hello and welcome. Today, we're diving into one of the absolute cornerstones of modern mathematics, the concept of a group. Now, at first glance, it's a beautifully simple idea, really just defined by four basic rules. But don't let that fool you. This structure is so incredibly powerful that it gives us a universal language to talk about symmetry itself, unifying everything from the integers we learn about in grade school to the fundamental laws of particle physics. So let's get ready to pull back the curtain on this amazing piece of mathematics.
So, to get our heads in the game, let's start with a little puzzle. What on earth could the integers, all the ways you can rotate and flip a square, and a Rubik's Cube possibly have in common? I mean, they seem totally different, right? You've got an endless list of numbers, a small set of geometric moves, and a puzzle that has driven countless people crazy. And yet, they all share a deep, fundamental mathematical structure. By the end of this, you'll see that the surprising answer is they can all be described as a group.
All right, here's our game plan. We're going to start with what a group actually is. You know, the formal definition. Then, we'll dive into some classic examples to make it all feel a bit more real. After that, we'll peek under the hood at their internal structure, see why they're so ridiculously useful across science, and finally, we'll take a quick look at where group theory is headed today.
Okay, first things first. What exactly is a group? At its absolute core, it's just a collection of things, any kind of things, along with one single rule for how to combine them. You can think of it like creating your own little pocket universe that has to play by its own consistent set of physical laws.
So here's the official starting point. A group is made of two ingredients, a set of things which we'll call G, and a rule for smushing any two of them together. We call that rule a binary operation. It could be addition, multiplication, or something way more exotic. But here's the first critical part. When you take any two elements from your set, let's call them A and B, and you combine them, the result has to also be in that set. This property is called closure, and it's non-negotiable. You can't use the rules of the group to somehow escape the group.
Everything, and I mean everything, about a group comes from just these four simple rules, or axioms. We just talked about the first one, closure. The second is associativity. All this means is that if you're combining three things, it doesn't matter which pair you combine first. The parentheses can move around. Third, you have to have an identity element. This is like the do-nothing element. You combine it with anything else, and that thing stays exactly the same. And fourth, every single element needs an inverse. This is basically an undo button. For any element you pick, there's another one that brings you right back to the identity. That's it. If a set and an operation satisfy these four rules, congratulations, you've got yourself a group.
Okay, I know those rules can sound a little abstract and maybe a bit dry, so let's make them come alive. Honestly, the best way to really get a feel for group theory is to just see it in action.
So let's start with an old friend, the set of all integers, with the operation of addition. Let's check our rules. If you add two integers, do you get an integer? Yep. Closure check. Is addition associative? You bet. The identity element? Well, that's just 0, because adding 0 doesn't change anything. And what about the inverse of an integer, say a? It's just negative a. They add up to 0, our identity. So the integers with addition? A perfect textbook example of a group.
Now for something completely different. Imagine you have a square. How many ways can you move it around so that it lands perfectly back in its original outline? Well, there are exactly 8 ways to do that. These are its symmetries. You've got 4 rotations, including the don't move it at all rotation, and you've got 4 flips, or reflections. This collection of 8 actions forms a group, which we call the dihedral group D4.
This grid, called a Cayley table, is basically the group's multiplication table. The operation here isn't multiplication, though. It's composition, which just means do one move, then do another. So for example, what happens if we do a horizontal flip, then follow it with a 90-degree rotation? The table tells us that's the same as doing a single flip across the counter diagonal. But, and this is a huge but, what if we did it in the other order? A rotation first, then the flip. We get a flip across the main diagonal. We got a different answer, and that little detail is unbelievably important.
And this brings us to a massive fork in the road. In our integer group, 3 plus 5 is the same as 5 plus 3. The order never matters. We call groups that have this property abelian, or commutative. But as we just saw with our square, a flip then a rotation is not the same as a rotation then a flip. Because the order matters, D4 is a non-abelian group. This single property, whether order matters or not, splits the entire world of groups into 2 fundamentally different kinds, and it's one of the most critical ideas in all of abstract algebra.
So now that we have a bit of a feel for what groups are, we can start to peek inside them. You see, groups aren't just uniform blobs of elements. They have this rich, beautiful internal architecture that we can explore. Oftentimes, you can find a smaller, self-contained group living inside a bigger one. We call that a subgroup. If you look at our square symmetries, those 4 rotations, they actually form a perfect little group all on their own. Now, what if you take an element from outside that subgroup, like a flip, and you apply it to every single one of those rotations? You get a sort of shifted copy of the subgroup, which we call a coset. In our example, doing that gives you the complete set of all 4 reflections. And here's where the magic really happens. If a subgroup is what we call normal, it's a special kind, we can sort of zoom out. We can treat the whole subgroup as one block, and each of its cosets as another block. These blocks can then form a new, simpler group. This is a quotient group, and it's like seeing a simplified, low-resolution picture of the original group structure.
Now, I know this can all seem pretty abstract, so why do we care? Why does any of this matter? Because, and this is the big reveal, the language of groups is the language of symmetry. And symmetry turns out to be one of the deepest, most fundamental organizing principles of our entire universe.
The applications are just mind-blowing. In physics, the standard model of particle physics, our best description of reality, is written almost entirely in the language of group theory. It's not a metaphor, it's literally groups. In chemistry, a molecule symmetry group tells you almost everything about its properties. In cryptography, the security of the entire internet is built on the fact that certain problems are really hard to solve inside groups. From understanding the shape of space in topology to number theory, groups are just everywhere.
This quote from the mathematician Richard Borchards just captures the wonder of it all perfectly. You start with these 4 short natural axioms, and somehow, hidden inside that simple logic, you get things like the monster group. And yes, that's its real name. It's an object with more elements than there are atoms in the sun, and it seems to exist because of a whole cascade of what look like insane coincidences. Its discovery was part of a project that created a kind of periodic table for all finite groups, one of the most monumental achievements in math history.
So to wrap things up, let's just take a quick glance forward, because the basic concept of a group that we've been talking about is really just the launch pad for even more powerful and sophisticated mathematical machines.
One of the absolute coolest extensions is the idea of a Lie group. Imagine a group where the elements aren't just separate little points, but instead form a smooth, continuous surface, like a sphere or a donut. Once your group is a smooth shape, you can suddenly bring in all the powerful tools of calculus. You can start taking derivatives and integrals right on the group itself. These are the groups that describe things like continuous rotations in space, and they are absolutely fundamental to modern physics. It's this beautiful marriage of algebra and geometry.
And that leaves us with this final kind of awe-inspiring thought. Group theory showed us that a simple, abstract idea like symmetry could be formalized into a precise language. And that language turned out to describe the deep structure of our reality. It just makes you wonder, doesn't it? What other fundamental patterns, what other hidden languages of our universe are still out there, just waiting for us to find the right mathematical framework to bring them to light?